Okay, seventh graders, I am going to go through our study guide. We're gonna start on question 1, which says a six-sided die is rolled 30 times. If the die lands with a 1 or 6 facing up, the player wins. If the die lands on a 2, 3, 4, or 5, the player loses. And it says consider this table of data collected on the right, which means this is our 30 times the die was rolled. So the first thing we have to do is find the experimental probability of winning and losing and write it as a fraction, decimal, and percentage. So I think with these, it's usually easiest to just start with the fraction. So the way that you turn a probability, an experimental probability, into a fraction is you have the number of favorable outcomes that were recorded in your experimental probability. Oh, I'm writing it over here. That's your numerator. And so that just means the outcome that you're looking for, how many times it happened. And then your total outcomes, which is just how many times you did the experiment, how many times you rolled the dice. So we know that we rolled the die 30 times. So our denominator will be 30. And then it says, what was the experimental probability of winning? We'll start there. So you win, to figure out how you win, when you roll a 1 or 6. A 1 happened 2 times, and a 6 happened 8 times. So together, that is 10 times that we won. It's the outcome we're looking for. So the experimental probability of winning was 10 out of 30. That's as a fraction. Now we also need to do it as a decimal and percentage. So to turn a fraction into a decimal, you divide your numerator by your denominator. So I would do 10 divided by 30, and then on the exam, you can use a calculator for this. It's going to equal 0.333 on forever, 3's forever, which we can indicate by putting a line over them. So that would be, so here we have it as a fraction, here we have it as a decimal. And then to turn a decimal into a percentage, you just move your decimal place 2 places to the right. So we would get 33.3%. And there it is as a percentage. So now to get the experimental probability of losing, we're going to do the same thing. We figure out how many times we lost, which is 4 right there for number 2. 6 for number 3, so that's 10 total. 3 for number 4, 13. 5 for 7 for number 5. So 20 times we lost. So remember, we put the outcome we're looking for, the amount of times that happened, as our numerator, out of 30 times total. And so 20 out of 30 is going to be our experimental probability of losing. To turn that into a decimal, we're going to divide our numerator by our denominator, 20 divided by 30. You get 0.6666 extending forever, which there's our decimal. Oh, put the line to show that it goes on forever. And then we move our decimal place 2 to the right, 66.6% as a percent. So that's question 1, or 1A. Now B asks us the theoretical probability of winning and the theoretical probability of losing. So when you're working with theoretical probability, you don't care about your recorded results. Those don't matter. For theoretical probability, we're just going to talk about the options that could happen and the options that could happen, and then how many satisfy what we're looking for. So for winning, there are 6 options for the dice, 1, 2, 3, 4, 5, 6. And since everything has an equal probability, we can just treat them all the same. So we think about how many of these allow me to win 1, 2. So I have 6 possible outcomes. And out of those, 2 are the ones that I am looking for, because those are the ones where I win. So, and you could write it as a decimal or a percentage, but as a fraction, the theoretical probability of winning is 2 out of 6. 2 outcomes satisfy winning, and there's 6 possible outcomes. So then we look at the probability of losing. There are 4 options in which we lose 4 outcomes out of 6 total outcomes. So the theoretical probability of losing is 4 out of 6. So now we're asked if the theoretical and experimental probabilities are different, and would we expect them to be? So first we'll start with, are they different? So since I had the theoretical, these are the experimental probabilities of winning and losing, it's 10 out of 30 and 20 out of 30. And now the experimental probabilities, or the theoretical, were 2 out of 6 and 4 out of 6. So these are different fractions, but they're actually equivalent fractions. This top one is equivalent to 1/3. The bottom one is equivalent to 2/3. And you can tell that because 6 goes into 30 5 times, and my numerator 2 also goes into my other numerator 5 times. So since the same number multiplies by my numerator and denominator to get this new fraction, that means that they're equivalent fractions. So in this case, my experimental and theoretical probability are not, or are the same. So are they different? No, they're not different. And would we expect them to be? So there's a few different answers that would work here, but I would think, so it's got to be something along the line. What you're looking for is that an experimental probability is usually not the exact same as a theoretical probability. If I flip a coin 20 times, it's usually not that 10 were heads and 10 were tails. So I wouldn't expect them to be. But the experimental probability is often close to the theoretical probability. So I would expect them to be close, and sometimes they would be exact. But probably more times than not, the experimental probability, when you've done something 30 times, would be a little bit different than the theoretical. So now, is the game fair or not? So there are a couple ways to answer the question of, is the game fair or not? In this case, all we know is the probability of winning and the probability of losing. That's all we know about the game. And so for a game to be fair, you would want the probability of winning to be the same as the probability of losing. It can go either way. In this case, and we're working with theoretical probability here. When you're determining if a game is fair, you use the theoretical probability. So the theoretical probability of winning we determined was 2 out of 6, or 2/6. And losing was 4 out of 6, or 4/6. So in this case, 4/6 is twice as big as 2/6. So you're twice as likely to lose as win. So we would say that that game is not fair, because the probability of losing is much greater than the probability of winning. And now lastly, are winning and losing complementary events? So complementary events, I'm just going to put it as CE right now, but those are complementary events. They're events whose combined probability is 100%. Okay, so that basically means either one would happen or the other. There's no other options. So we can look at our probability of winning was, and you can do it as a fraction, a decimal, and a percentage. So I'll show you all. So when you're doing it as a fraction or a decimal, I guess I should add this here. Instead of 100%, remember that a percent is like 100% is equivalent to 1 when we are looking at a decimal or a fraction. So it's either the combined probability is 100% for using percents, or that it's 1 if we're using a fraction or a decimal. So 2/6 plus 4/6 equals 6/6, which is equivalent to 1. So they are complementary events. And if we were to do it as 0.33 plus 0.66, which are decimals, equals 99%. This is a little tricky. This is why I like to use fractions usually for complementary events. It's only 99% because we round it. Since the 3s and the 6s go on forever, this is actually 0.333, 0.666. They add to equal 0.999. It's basically 1, it counts as 1. Or 33.3% plus 66.6% would equal 99.9%. So are they complementary events? Yes. Only one or the other can happen.